Hi, my name is Bridgette Sparks. I teach chemistry at Saline High, and I'm very honored to have been selected as a semifinalist for this award, and wanted to thank you for taking the time to learn more about my teaching practices. I found it really difficult to pick which instructional methods I was going to highlight in this video, as I have a lot of different techniques. But the one constant is I want my kids to be engaged in the learning process. They come through the door and they think they're going to be wowed by some sage on the stage as if they're an empty vessel to be filled. But I truly believe learning happens when they can construct their own knowledge, and then we can modify that. Given the short time I had with you on this video, I try to pick lessons that truly exemplify that. But given that, the classes that made the most sense, given some family illness and winter break and all these different things, I had a very short time. The class that you're going to see, I've had about 2 weeks of FaceTime with, and therefore the trust isn't there to participate fully. It was like pulling teeth to get them to participate. But even in 2 weeks' time, that's going to change quite a bit. But I did think that these lessons best exemplified my teaching philosophy, and so I thought they were the best ones for the video. Talking about that teaching philosophy. My goals as a teacher, I want to help kids to analyze. I want them to problem solve. I want them to take personal responsibility for their learning, and therefore be able to design their own experiments. Once they've designed those experiments, to fully be able to articulate their understanding with clear lines of reasoning, whether it's written or orally, and then to see the connections between work and life. So you're going to see two portions of lessons. The first one, we were contacted by Austin Powers himself, and he needs help making 2 grams of an antidote that is going to combat Dr. Evil's sinister plan to stop us from texting. And the kids are just given that learning goal. And they're not told how to do the calculations. They have the background knowledge. That's what we spent the last 2 weeks learning about. And they don't have the procedures given to them. They're going to design their own experiment. And the key will be, how do I isolate that product, because there were other products made in the experiment. Once they have come up with a set of procedures, I asked them to really think about ways of minimizing the error. And that's the great thing with them designing the experiment. They take full ownership over that process and really think about what they're doing, instead of cookbook chemistry where it's like, let me just mindlessly follow direction. Then, after they've done the experiment, they're going to write a letter back to Austin Powers, because we have lots of different forms of communicating with peers or people that contract us for work, whether it's emails or scientific journals. And so they get that opportunity. In that letter, I want them to cite their findings and then explain the process. And that process needs to be clear and reproducible. And then in some activities, I have similar activities to this, they actually invoice the company. But we decided to give Austin Powers a break, and it was free of charge this time. All right, so class, today we're doing a lab, right? And as you know, my expectation is that you prepare for that lab, right? So you all read the letter, but again, for the sake of our video audience, we will have someone read our letter with dynamic speaking. Anybody, any volunteers? Awesome. Can you see from there, or do you need to come up?
Okay. Dear chemistry students, it has come to our attention that the evil Dr. Evil has determined that he can indeed rule the world forever unless a dedicated group of high school chemists can come to the rescue. Evil has created the what?
Insidious?
Insidious chemical xanthopene trifosfate.
That's pretty good.
Which causes victims to develop small growths on their fingertips that make it impossible to tap any keyboard, including text messaging, computer keyboards, and MP3 players. No texting. We must stop him. We heard from the ceramic artisan company that you are groovy lab technicians, and we'd like to recruit your help to take down Dr. Evil. Your mission: create enough antidote, resulting salt, that will prevent the population, including you, from contracting painful psoriasis. Upon failure to take over the world through xanthopene trifosfate, Dr. Evil will most likely give up on this idea, giving us more time to capture him and save the world. Thank you in advance for all your hard work. Good luck with your mission. Peace and love, Austin D. Powers.
Awesome. Thanks, Tabby. All right, so what you'll be doing today is trying to come up with that antidote, right? And so this is kind of the culmination of our unit, and if we think about it, right, we've already talked about our goal. Let's make the antidote, the resulting salt. But let's talk about the different skills that we have that we're going to use today in order to solve this dilemma. Right? So what are some of the skills that you're going to bring to the table today? Yes?
Like measuring different liquids.
Okay. Our accurate measuring. Jacob?
Stoichiometry.
Stoichiometry. What let you know that we needed to use stoichiometry?
Just figuring out how much ingredients we're going to need to make the 2 grams of salt.
Okay, yep. So we heard that we need to make 2 grams of resulting salt. So we need to figure out how much of the ingredients. What else? It might be related to some of these things, like stoichiometry. What are some things that you need to be able to do that successfully?
Calculate theoretical masses.
Okay. Theoretical masses. And you're going to be given different reactants. Each table will have a different reactant. But not all of them are going to be solid. So you won't be finding theoretical masses for every reactant. What are some other forms of, or other ways of measuring out quantities of reactants?
Volumes.
We can look at volumes. Yeah. So we might need volumes instead. All right. Anything else? Yeah.
Like finding molar mass.
Okay. Finding molar masses. Yeah. Kathleen. Balancing chemical equations. So that will be the first problem that you're going to have to solve, right? How do we figure out how much starting material to produce that 2 grams of salt? But that's not the only problem that you have before you today, right? You have to be able to isolate that 2 grams of salt. So you're going to have to look at the other products that are formed and figure out how do I extract those other things, and I'm only left with the salt, right? So you're going to have to think of some of your lab experiences in Chem A and use that as well. So what you're going to do is you're going to come up to me with a set of procedures. After you've done your calculations, you'll come up with a set of procedures, and I will verify those before you get started in lab. And so what are some things you want to think about when you're communicating to someone else about what you need to do? You want to be? Yeah, Logan.
Precise in like the amount of things or materials we need.
Okay, precise in terms of the amount of materials we need. We want to be safe for sure, right? So most definitely, what will we need to do today?
Put our goggles.
Put our goggles. And you remember my goggle policy? Anybody remember the goggle policy? Adam? Goggle marks are good. Yes, that is one. But the policy itself, I will warn you once, right, if your goggles are off, and then on the second time, what happens? Yeah, you get a 0 in the lab and sit out for the day, right? Having that kind of strict policy helps to eliminate the playing with your goggles. Just leave them on your face, right? All right, and there might be some others that will, once you come up with your set of procedures that we'll talk about, that might be more specific to what's being carried out in lab. All right, and then the other thing I want you to consider when you do come up with those procedures is ways of minimizing error. Every step that you take today, I want you to think, how can I make sure that I end up with 2 grams of salt? No more, no less, right? In every step that you write out today, right? Consider that. And then we'll talk about it at the end of lab, what those things were. And sometimes it comes out of experience, right? You'll do something in lab like, wow, that shouldn't have happened. I just lost material, right? But you'll learn from that mistake, and then the next time you have the same procedures, you'll know what to change. Cool? All right, so when you're done with the lab, there is another aspect, and that is writing up the lab. And so we need to be able to communicate what we did. Being able to do it is one thing, but if you can't reproduce the results and you can't communicate that to someone else, then it's no good, right? If we found the cure for cancer, right, but we can't articulate how we found that cure, it's not going to be useful to the scientific world. So we're going to get a little bit of practice with that. You're going to be writing a business letter back to Austin and tell them what your findings were and how you came up with those findings. Because some of you probably don't have that practice of writing business letters, there's a rubric there that will help you figure out what should be the meat of the lab, right? Meat of that business letter. And this is what we do in the work world, right? In the science community, that can come in two forms. We can either write a scientific journal article, right, to, let's say, Science or the Journal of ChemEd or whatever that newspaper or article might be. But that's not the only form we take. Oftentimes it's with a company, right? You might be doing work for a company and you need to communicate things, and those might take the form of letters or emails. And so I want to give you that experience of articulating yourself in written form. So if you have any questions, though, when you're going through that process, don't hesitate to come to an office hour. You ready? Ready to start that lab? All right.
Maybe we need this, but this
Well, think about minimizing error, right? You don't want to use any of your salt, so where should the mixing occur? If you mix them in the beaker, are you heating it in the beaker? Yeah, so think about that. Can you introduce air if you mix in a beaker? Because then what do you have to do with the stuff that's in the beaker? You have a ceramic dish at your table called an evaporation dish if you didn't use it in Chem A. And then the Bunsen burners, if you look at your lab bench, there's going to be cabinets that hug your lab bench. One of them says burner. In that cabinet, you should find a Tupperware box that says burners, and in there you should find your strikers, your Bunsen burners, and the hoses to attach it to the gas outlet. All right? Thanks. For trying to balance -1 to get to 0. Does that work? Go through this lab and try to minimize error as much as possible. So the question is, do any of these steps create error, right? So when you mix them together, I noticed you're mixing in the evaporation dish itself, right, instead of in a beaker, right? Why did you choose to mix them in the evaporation dish itself? Very good. Yes, the more we transfer things, as she said, the possibility you're going to leave some of it behind. So that's a great way of minimizing error, right? So I want you to go through every step and think about how could this introduce error and what can I do to combat that? I don't want error in my lab. I want my 2 grams of antidote, right? Someone's life is at stake, right? So there's a couple other steps in here that might introduce error, and you need to think about what am I going to do. Cool. In the second lesson, they are going to construct their own set of rules for naming. I give them a data set, and they need to figure out the similarities and differences between the chemical names and the corresponding chemical formulas. And then as a class, we actually check those rules. So if a student provides one rule, does the data set support that? And if it doesn't, how can we tweak that rule, or do we need to completely start over? And then it really gives them an opportunity to analyze. And then I do come back the next day because some students, it's such a different teaching style that they struggle. And as I said, it takes a year to get them on the same page as me sometimes. I do come back and we talk about it a little bit more explicitly with a little bit more structure for those kids that struggle with that. But they do have an opportunity to really look at data and how we need to make claims, support those claims, and explain our reasoning. So thank you, and I hope you enjoyed the video. Great. Okay, so we are going to go over naming today, but instead of teaching you it directly and saying, okay, these are the rules for naming, memorize them, go home, learn them. Instead, I like to teach it in a way that helps you with your problem-solving skills and your analysis of data. Because truly, in whatever you do, whether it's the sciences or in business, data is important. It drives what we do. And for instance, if you're in marketing, right, and you were a buyer for a certain company, you would look at sale trends to figure out, wow, should we be pushing the hot pink shirts or the teal green shirts, right? And so that kind of analytical thinking does take some practice. So we're going to get that practice today. So what I've given all of you is a data set, and that data set is reflected on the board so our studio audience can see what we're looking at. But this data set has a number of chemical formulas and their corresponding names. And I'm going to give you about 10 minutes to look through this data set and try to come up with rules that govern this naming system, right? And then we're going to, after that 10-minute time, we're going to come together and state some of those observations. And what I want us to get in the practice of is actually using evidence as support. So if I say, let's go back to that marketing example. If I say, well, I really think that we should purchase a lot of pink shirts this year, right? That's what we should buy for our company. I would have to support that statement, right, with some evidence to confirm that that's what we should be doing. So we might look at the sale trends of different colors and hopefully, if I'm doing my job correctly, right, the pink shirts were the ones that sold the most, and that's why we're going to continue to buy those, right? So when we do state these rules that you've come up with, you're going to cite the evidence from the data set that proves that. And then we'll see if there's any data points that actually contradict your rule. And if it does, what do? If someone comes up with a rule and some of the data supports it, but some of the data doesn't, then what are we going to do to that rule? Raise a hand. Yes?
We'll go back and redefine the rule, like change it to see what will make it work for both.
Yeah, so if you didn't hear her, what she said is we'll go back and we'll change that rule so that it incorporates all the data points and it's correct then, right? And that's what science is. Science is very dynamic. It is ever changing. Sometimes I think we read textbooks and we're like, oh, well, this is very dogmatic. It's never going to change. It's always been this way. But if we think about the atom, right, you've already learned about the structure of the atom. Hasn't that changed quite a bit over time? And it's continuing to change, right? And so it is okay to go back, edit rules as more data becomes available. Cool? You ready? So I should hear lots of talking. Talk it out with your friends nearby. This definitely shouldn't be an isolated activity. So again, I'll give you 10 minutes and then we'll come back and see what we came up with. Great.
Because it has an 86 carbon hydrogen. Five is just one, and then after is. But I never know for when there's a transition method, it's got to whatever.
Okay, let's move on to some different observation. We're getting a little quiet in here, so lucky for me, I still have my cards. All right, Jack, someone I haven't heard from. Jack, anything else you notice?
Some of them have like copper 2.
Okay.
And when they have that, the 2 switches to the other atom.
Okay. So I'm sorry. So give me one of your examples that are leading you to say this.
Copper 2 chloride.
Copper, and is that 2 a number 2, a?
2 in parentheses.
Okay. And it's in Roman numerals. Copper 2 chloride.
Yeah.
And the formula for that is?
CuCl2.
Okay. Great. And what was your observation?
That the
Okay. So you think the Roman numeral, it is after the copper, but it seems to correspond to the number of the other one. So you hear his rule? He's like, that Roman numeral is going to tell you the number of the other atoms in the formula. Do you agree with that?
Another example is tin 2 oxide.
Okay.
You said the charge of the tin is 2, but the oxygen substitute is
Oh, okay. What is the formula in tin 2 oxide? SNO. So yeah, that data point does suggest that that rule needs some tweaking. We don't necessarily have to throw it out, right? It can refer to number of atoms, or it can refer to something else. That's what we have to figure out. Andrew?
It refers to the charge of the transition metal.
So okay. So he's suggesting it might be the charge on the metal. All right. So earlier we were told that charges are going to balance to 0, right? And we said we would check back with that and see if that was the case. So we can do that now and verify that this is a charge on a metal. Yeah, Tabby.
I was going to say all of those are, like the first one is a transition metal.
Okay. And when you say all of those,
I mean all like lead, 2, sulfide, or cobalt, 4, chloride, those are all things, those are both, the lead and the cobalt are both transition metals.
okay. So she's saying that all the ones that have Roman numerals are the ones have transition metals. Is there anything to suggest otherwise in that data set? Boyd, notice anything in that data set to suggest otherwise? He doesn't think so, but let's go with one more. Adam, what do you think? She's saying all the ones with Roman numerals have transition metals in them. I love it. He's checking to make sure. He's not going to just say.
That's what I think, yes.
Okay. How many of you agree with that? Oh, cool. Majority of us. Great. Okay. So now let's go and verify the other statement that it's the charge on the transition metal, right? If the charge on tin is a +2, and we look at the periodic table, what do we find the charge on oxygen to be? -2. So the ratio would be, if in fact the charge is +2, what would the ratio be? 1 to 1. Is it 1 to 1? Yeah. All right, let's check this one. So if copper is a +2, because the Roman numeral is stating the charge, chlorine has a charge of -1, but there's 2 of them, right? Would that balance to 0? It would. But let's just go one more example further in order to confirm our rule. Can someone give me one more example? Iron chloride. What is the Roman numeral in iron chloride? Iron 3 chloride. So let's actually try to figure out what the formula should be and see if it matches our data set, right? So we're trying to come up with a prediction. So iron, if iron has a +3 charge, and we said earlier chlorine has what charge? -1. What should the ratio of iron to chlorine be? I'm sorry, loud and proud? Okay, I heard 1 to 3, right? 1, and we don't write 1s to 3. Is that the formula they gave you on the sheet? 1 iron to 3 chlorines? So our data set does support that this Roman numeral stands for the charge on the transition metal. And why does that make sense? What do you know about transition metals that you learned before? Yep?
Charges can change.
Yeah, their charges can vary. They don't have one set charge, right? We have iron with a +3 charge. There's also an iron with a +2 charge. So how do we know the difference between those two formulas, right? They'd have to tell us that. Great.